Good afternoon, everybody. Welcome to Exciting Afternoon of Chem 1105 with your host, me, Dr. White. All right. One of the reasons I was running late is the following that I just posted. If you look on your screen, and let me check to make sure. Yep, that's what you should see. I just posted, you can see the time I just posted about test number 2. Now, a week from today, on the 13th of this month, 7/13/23, I will be giving test number 2 online. I'll download the password protected PDF file for test number 2 from the assignment area Blackboard on Thursday. That day at 8 a.m., I will send out the password for test number 2. You have until Friday, 4 p.m. to finish test number 2 and upload your answers as a single PDF file to the assignment area Blackboard. If we are face-to-face, test 2 takes 40 to 45 minutes. Take 2 hours. If you need a little more than 2 hours, take it. But make sure you have it uploaded by the deadline on Friday. Now, test number 2 will cover Chapter 4 and Chapter 5, Part 1, which I should finish today. This will cover chemical bonding, including ionic and covalent chemical bonds. It will cover mole and mole-related topics, including balanced chemical equations. Oh, by the way, I will have problems where you have to balance chemical equations. On my test, the answer it's already balanced will never, ever be correct. I'll say that again. On my test, in the final 2, if I ask you to balance a chemical equation, the answer it's already balanced will never be correct because you're going to have to balance it if I ask you to balance it. I just think that's it's fair. Now, test number 2, the test has 18 problems on 9 pages. There are no multiple choice, but some of the questions have multiple parts, like part A, B, C, and so on. Now, for the topic area, it will have 50 points on chemical bonds and related topics, like Lewis structures and both elements and molecules, and ionic and covalent bonds. And it will have 55 points for mole and mole-related topics. Now, if you notice, that adds up to 105. And guess what? There's five, yes, 5. Yeah, I got 5 fingers, 1, 2, 3, 4, 5 extra bonus points. Don't tell anybody I'm being nice. Shh. But 5 extra bonus points. Now, you will definitely need a scientific calculator for this test. If you don't know how to use a scientific calculator, 1, watch the video, which I did. I don't know the link right now, but I'll have to find it and I'll send it out. Or come to my office hours and I'll help you out. All right, now listen carefully. I reserve the right to subtract up to 50, yes, 50 points for anyone who doesn't follow instructions. That means upload things as a single PDF file, or anyone who does not upload your test. Ooh, that should be test number 2 answers. Sorry about that. I'll have to change that. On time as a single PDF. I will be posting test number 2 scores the following Sunday after the Friday, which would be, let's see what date that is. That would be by the 16th or earlier. By the 16th or earlier, that's Sunday, 1 p.m., I will be posting your test number 2 scores in Blackboard. At that time, I will post an announcement and send an email to all of you that your test number 2 score is in Blackboard. I will also email each individual student, just like I did for test number 1, the points you receive for each problem and each part of a problem on test 2. Now, on the Monday after test 2, which I think that's the 17th, but that Monday, I will go over the answers for test number 2 in our Zoom meeting, but I will delete this, cut it out from the Zoom meeting YouTube video. However, just like I did for test number 1, I will create a private YouTube video with the answers for test number 2, and I'll send you the URL link for that video. On next Tuesday, I will do a review for the material on test number 2 in our Tuesday Zoom meeting. And the Thursday of the test, we will have our regular Thursday Zoom meeting. And by the way, have a nice rest of the week. And that's the information for test number 2. Remember, it's a week from today, the 13th of July. Wow, it's already the 13th. Boy, where's this year gone? But anyways, the best way to study for any test, especially test number 2, is do the practice problems. Do the practice problems for chapter 4. Do the practice problems for chapter 5, part 1. If you can do those all correctly, you'll do good on test 2. If not, come to my office hours. I'll have it on Monday and Wednesday next week at night from 7 to 8 p.m. And if you need extra help, email me and I'll see if we can set up a Zoom meeting where I can help you out. I've already done that for some students already. All right, any questions on test number 2? Remember, a week from today. Julia, I don't know. I've never used the Acrobat drawing tool. How easy is it for you to write like I've done in the problems, setting them up? If you can do that, that's fine by me. I know, but it's one thing to use a pen or pencil to draw things, or like I have with my drawing pad, but to use a mouse to draw things might be a little more challenging. If you can, where I can read it, I know what you're talking about, the tools. I'm just saying, how easy is it for you to do it clearly so I can read it? If you can read it and think I can, fine, I have no problem. If not, if you don't have a printer, remember, all you have to do is take a piece of paper, write down the problem number and your answer. You do not have to rewrite the question. I know them up here, and I also have the actual test. I can go back and look at it. What was that question? But anyways, I have an answer key. So if you want, try any way you can put your answer on. Now, one thing I will give advice, especially for test number 2, show your work. If you make some sort of mistake, like a math mistake, if it's an 8 or 10 point problem, and there are some 8 or 10 point problems, if you don't show your work and just put down an answer and it's wrong, you get 0 points. If it's, say, a 10 point problem and I say, oh, you made a mistake there, math mistake, I'll take off 1 point. If it's a problem where I say, oh, you made this mistake and that part of it, but the rest is right, well, if it's a 10 point problem, I can give you 6, 7, or 8 points. And that's a lot better than 0. So on my test, it always pays to show your work. All right, any other questions? All right, let's go through today's game plan. What we're going to do is the lab that we'll do today, and then we'll go back and finish Chapter 5, Part 1. Now, about the labs, make sure you hand them in. I extended the time for the labs last week and Monday because of the 4th of July holiday, but you have to hand your labs in. So please do. Acrobat came out with a new format, and I'm trying to get used to it. I think it's nice, but anyways, let's take a look at today's lab. Today's lab is called separation of a mixture. A mixture is where you have different substances, also known as chemicals or elements, mixed together, and each one retains its own chemical identity. They don't react with each other. Don't forget, in all labs, you should wear your goggles, your gloves, and if you want, an apron. And I would highly recommend, like I always do it in one of those aluminum inexpensive pans. Now, here they talk about atoms, elements, and all that. Now, let's talk about mixtures. Now, mixtures are when you have elements and compound added together, as I just said, without reacting with one another. And the mixtures can be homogeneous, the same throughout the composition, or heterogeneous, not having a uniform or the same throughout the composition. Homogeneous, as I've used, the air we breathe. And if you take, and I've used this one too, salt and water, or I've used sugar and water. Now, heterogeneous, and I use this, they don't have it here. If you take sand and water, like I'm not going to put sand in here, and you mix it like this, the sand will go to the bottom, separate from the water, which will stay up here. And that would be a heterogeneous mixture. Now, how do you separate things in a mixture? Well, you use physical properties. And you can separate different things based on their physical properties. Now, the mixture you're going to be using has iron filings, that means little pieces of iron, silicon dioxide, which means sand. And by the way, Dr. White is an expert in sand because one company I worked at, the product we made was to glue sand together to make the molds for foundries that make things like your car engine or somebody else's car engine. Some of my more, how should I say, unique experiences and memories. One, because of a problem that I had to solve. And once I did, I was asked to come to the Saginaw, was it Saginaw? I think it was the Saginaw General Motors Saginaw foundry. And that foundry made V8 and V6 engines for cars. And that site, the foundry, was about 5 or 6 times larger than the main campus of COD. It was huge. And I gave a talk to the senior people at that foundry, how I saw the problem they're having with the product that our company sold them. A lot of money involved, lots. And that was sand they were using. And I know about different types of sand Most people don't. But anyways, speaking about that, I also was invited to the Ford Windsor foundry where they made also car engines because I developed a new product that worked better in holding the sand together, but at the same time was more environmentally friendly because when you put the hot metal in that mold with the sand and the glue eventually burns off. And if it's not that environmentally friendly, it's not that healthy. It doesn't smell that good. And when they started using my new product that I invented, as my last US patent, when I was at Borden Chemical, the neighbors who lived near the foundry started calling and thanking them because it didn't stink as much anymore. But let's talk about your lab today. You'll be using iron filings, sand. Oh, I got sidetracked by sand, benzoic acid, which is an organic chemical, and sucrose. Sucrose is an organic chemical, but you know that as table sugar. Now, if we look at table 1, we can see key physical properties. The iron and sand are not soluble in water. The benzoic acid and sucrose, otherwise known as sugar, are. But if we look at the solubility at different temperatures, well, the iron and sand are not soluble. That's why they have Na not applicable. But if you look at benzoic acid, when the water is cold, 0 degrees C, it's barely soluble, 0.17 grams in 100 milliliters. But at that same cold temperature, the sucrose sugar is extremely soluble. Now, another thing is it magnetic? Can you take a magnet and will it stick to it, attract to it? And the iron, yes. Sand, no. Benzoic acid, no. And sugar, no. Now, the last thing they show you is the melting points, temperature in which a solid becomes a liquid. And sometimes you can use that to separate things. Now, if you notice the iron filings or filings, I guess it's the right way of pronouncing it, and the sand, silicon dioxide, have a high melting point, really high. In Fahrenheit, that's over 3,500 degrees Fahrenheit, not a temperature you're going to get in your house. And even the other two are very high temperature, a couple hundred degrees Fahrenheit. So that's not going to be for this lab, the temperature, melting point temperature, will not be a physical property we'll use to separate it. All right, let's look at the overall scheme of what you're going to be doing today. You're going to be using a magnet to separate the iron filings from the mixture. Once you do that, what's left, you'll dissolve in water. The benzoic acid and sucrose will stay in the water. When you decant the water, the sand, which is insoluble, you can separate. So we've now separated the iron fillings and the silicon dioxide. Now, how do we separate the benzoic acid and the sucrose? Well, we use this property right here, the difference of solubility in cold water. And you'll use low temperature water. The sucrose will stay in the water, but the benzoic acid will precipitate, fall out because it's not soluble. And then using what's called a funnel with filter paper, you can separate them. Now, here's the equipment you'll be using. Now, unfortunately, I couldn't find most of this other than I don't know where I put it. I'll find it tonight or tomorrow. It'll be too late, but you'll be using all this equipment. Remember, you have the large plastic beaker. You'll need 2 of these foam cups. You'll need this funnel. You'll need a ruler. graduated cylinder, your balance, the weigh boats, which I showed you. You bend the ends up, you can empty it, but you'll do that. Now, in the balance, remember when you turn it on, it should read G on there. And to zero it, when you put the weigh boat on there, or if you just the weight of it, whatever, before you weigh anything, the button on the right says tare, which will zero it. Now you'll have filter paper, you'll have a bottle which has the sample mixture, your plastic spoon, and your thermometer. Now, they say use distilled water, you can use tap water. You need some ice, you'll need some plastic wrap, a small piece, a small bowl, or you can use one of those Ziploc square containers, food containers. You'll need a heat-resistant surface, such as a stovetop, or they say a trivet, something to protect wherever you are, a timer, and your camera. All right, again, wear your safety goggles and gloves, and the apron would be a good idea too. Now, in this lab, you're going to be heating water to 75 to 80 degrees C. That's hot. You do not want boiling water. I'll say that again. You're going to be heating water either in a microwave or on the stove. Be very careful when you do it in a microwave because it will bubble up and go boop, and it could do that in your face or in your hands. So be careful. I like doing water. I never ever boil water in a microwave. I'll do it on a stovetop, and I have a very good microwave. Had it for a number of years, Panasonic. But I'll hit a lot of other stuff, but never boil water in there. Now, you should wear some sort of hand protection like oven mitts or pot holders when handling the hot water and the containers the hot water is in. Now, the benzoic acid, it has a health hazard, meaning you don't want to get it on your skin because it'll irritate it, and it's hazardous if you ingest it. Don't. You should not be drinking, eating, or chewing gum while doing this activity. Wash your hands before and after. Like I told you, you can tell a chemist, organic chemist, especially when they go to the restroom, if they've been working with chemicals, they'll wash their hands before and after. And here they remind you, which I forget, keep pets and children away from the lab material and equipment. All right, let's go through what you're going to do. First of all, on your balance, put the weigh boat, tare it, place the weigh boat and zero it with the tare button. Open the packet and slowly dispense the material and record the mass in there. I don't think they tell you how much, but I at least do 5 grams. I don't know if they gave you 5 grams. But anyways, remove the weigh boat and its contents. Now, while it's still in the weigh boat, take the magnet and put the plastic around it tight, and then run the magnet all the way through, all around. And then take it out, the magnet, and over the second weigh boat, which you tare first, hold the plastic and the magnet, and with the plastic still over the weigh boat, remove the magnet and tap the plastic a little, and all the iron filings will go into the weigh boat, which you can record. Now, here for step 6, measure the mass of the empty plastic beaker and record it in table 1. Pour the remaining sample from the weigh boat. Remember, bend the corners and you can tap it right into the plastic beaker. Put in approximately 50 milliliters, and you can use the regular water, in the graduated cylinder and transfer it to a pot on the stove and heat it to about 70, 75 degrees C. You do not You do not want to have that water boiling. Now, once it's at that temperature, remember, have extra protection on your hands, pot holders. Add the hot water to the beaker with the mixture, swirl it with your spoon, and let it stand for 2 minutes on a heat-resistant surface. I have the silicone pads for that, or just put it somewhere. Well, I don't know if you have I have open grates on my oven range, so that would be, but put it on a surface that has some protection that's heat resistant. While the benzoic acid are dissolving, in other words, at 2 minutes, make an ice bath in a bowl or a container that's about 50% ice cubes, 50% water, approximately, and fill it about halfway with ice and then cold water, 50-50 mixture. And here they say just enough till the ice cubes start to float. Now, pay attention. Decant all the liquid from the beaker into a foam cup. Then set the beaker let's see. All right. Decant all the liquid from the beaker into a foam cup. Now, when you decant it from the beaker, the plastic beaker, the sand should remain behind. You want to do it slowly so the sand stays in there. Now, there might be a little water at the end, and then you can take your spoon, if necessary, to get any more liquid, not solid, not the sand. Now, in the plastic beaker now, you have the sand. Put that somewhere safely in your kitchen, away from children and animals, your pets, so it can dry overnight. Now, in the foam cup, you now have a liquid that has benzoic acid and sucrose. You'll put that into the container of the ice and water. Make sure the water doesn't go over the lip of the cup, and make sure the cup doesn't spill over. You might want to hold it and let it cool for about 10 minutes. And then you'll see something neat. You'll see these crystals form and go to the bottom. And they have taking a picture, you only have to take one during it. Now, here, and I couldn't find my filter paper, you take the filter paper, which is a round circle, fold it in half. And then you take that half circle and fold it again. And if you pull one of the edges out, you'll have a cone that fits in your funnel. Now, take another cup, and you can use any plastic cup they give you. Here they have, it's frosted. You actually, in your kit, it's clear, I believe. And what you'll do is record the mass of the second empty cup, hold the funnel over it, and pour the liquid into the funnel. And swirl it so you get what you're pouring out of, so you get all of it, including the solid, into the funnel. And be patient, let it all drip down into the second cup right here. And then what you'll do is take the filter with the solid. Now, before you pour anything in there, make sure you lay the filter paper dry. And then you'll have a solid in there. Put that on some aluminum foil or plastic wrap somewhere safe. Let it dry overnight. And then you'll weigh the filter paper and the solid in there. Now, in step 20, you're going to let in the second cup, which now has the liquid, you're going to let that evaporate. It may take a day or so, and you'll weigh, by the way, you should have weighed that second cup empty, and you'll weigh it after it all is evaporated. So if we look at table 1, you'll be doing all these weights, and then based on math, you can figure out what is the weight of the iron filling. That's the mass of the weight of the iron that was in the weigh boat that was tiered up here. The sand will be the weight of the beaker and the sand minus the weight of the beaker after it's all dry. Now, the filter paper and benzoic acid, the benzoic acid weight will be the weight of the filter paper and benzoic acid once it dries minus the filter paper. That will give you this benzoic acid. Then the sucrose will be the weight of the foam or the plastic cup minus the foam cup weight. And that will give you the weight of the sucrose. Now, if you add up the weight of the iron filings, the sand, benzoic, and sucrose, you'll get a total mass of components. Now, originally, you had a weight of the sample. And percent covery is, I'll show you on the other, in your write-up. I thought I had it. Well, let's, hold on. I just did something I didn't want to do. Here it is. Percent recovery is the total mass of the components divided by the original mass of the mixture times 100. And, there are only 4 questions, so why don't you answer all of them? And by the way, 2 of them are 2-part. They ask a question: which chemical in the separation do you believe was the most accurate to the original mass in the sample? And then they ask a second question: why? Which really they're asking, what's the reason you picked that chemical? Same thing for number 4. What was the least accurate? And they also ask why. So make sure in 3 and 4, you answer both which chemical and explain what was the reason you used it, picked that chemical. And I think we're not in screen sharing. So here's where you'll have the lab report. Fill out table 1 and 2 and answer that. Now, this is going to take a little time. So prepare, make sure you wear proper equipment, especially with the hot water. You don't want it boiling because it could melt. You use the regular plastic cup, melt it, and you don't want that to happen. Now, one of your colleagues just asked a great question. In the labs, they have you take 1 million photos. I only need 1. Give 1 selfie of you with some of the equipment or whatever of that lab. That's all you need to put in with the lab. Either have it embedded in the PDF file or the Word file, or upload your picture as a separate picture file. You're welcome, Yulia. All right, any questions besides the one that was already answered? All right. Let me close a couple things. Let me open something important. And let me open up one other thing that's important. All right, yesterday and the day before, not day before, but Monday, we're talking about mole relationships. And I'd highly recommend you all look at test number 2, important information. These are things I will give you for test number 2. Now, yesterday we were practicing these 3 concepts, and we actually moved on by that. Well, let's go back and look at 1 mole equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights of that compound. And that reminds me, I better open up a periodic table too. All right, let's do a little practice. All right, the question is how many moles of H2SO4? This is a very important chemical. This is called sulfuric acid. And near the end of the semester, we'll talk about sulfuric acid and other acids. But how many moles sulfuric acid, H2SO4, are 578.6 grams of H2SO4, sulfuric acid? So let's do it stepwise. First, what are you being asked to find? What are you given? Your turn. All right, it's now my turn. We're trying to find how many moles of sulfuric acid. What are we given? Well, how much sulfuric acid we have. Now, the only number we have is this number. So that's what I'm going to start with. Now, if we had a ratio that can convert it, what units do we want our answer? Your turn. All right. And the answer is, well, we figured that out right here. We want to get the units of our answer to be moles of sulfuric acid, H2SO4. And now, what units go on top and bottom of that ratio? I'm going to let you do it first. I'm really going to share today. See what a nice person I am? And it's now my turn. It's time to use your good buddy, your good friend, unit analysis. And whatever we're trying to get to, the units go on top. Whatever we're trying to get rid of, we don't want grams of H2SO4 in our final answer, that goes on the bottom. Oops, wrong color. And where do we find a relationship between moles of a compound and grams of a compound? Well, if you look at important information, test number 2, 1 mole of a compound equals the molecular weight of that compound in grams. Oh, I didn't give you the molecular weight. Well, it also tells us that the molecular weight is the sum of all atomic weights. So now how do we do that? We look at our periodic table. And we need hydrogen. And remember on test 2, and I'll say on test 3, 4, and the final, underneath your name, it will say, please use proper significant figures for all calculated answers. It will also say, please use 3 significant figures for all atomic weights. And if you don't, I'll take off a point. So hydrogen is 1.01, the 3 significant figures. Oxygen, 15.999, no, 16.0. And sulfur will need the 3 significant figures is 32.1. So for every 1 mole, we need the molecular weight of sulfuric acid. And the molecular weight, H2SO4, 2 hydrogen, 1 sulfur, 4 oxygen. 2 times 1.01, 1 times 32.1, and 4 times 16.0. Now this is 2.02, 32.1, and 4 times that would be 64.0. We add it up, and hopefully I did that right. If not, somebody will correct me. I think I did. Now, when you do an addition, you have the same number of significant figures to the right of the decimal as the number that has the fewest significant figures to the right of the decimal. And all numbers, 0 included, are significant to the right of the decimal. This has 2, this has 1, this has 1. So the lowest number is 1. So now we have to round this off to 1 significant figure to the right of the decimal. I'll keep the 1, use the 2 to round off. That's 4 or less, so I'll drop it. So the answer for the molecular weight, sulfuric acid, is 98.1. And that's 98.1 grams is 1 mole. Now, before we pick up our calculator, actually it's hiding over there, I'll look at my units. Notice grams of sulfuric acid divided by grams of sulfuric acid. And anything divided by itself equals the number 1 and cancels out. So this cancels out. I'm left with moles of sulfuric acid, H2SO4. Yes, that's what I want. So now I can happily pick up my calculator, turn it on, clear it. And divide 578.6 by 98.1. And my calculator gives me this number. Are you ready for this? Times 10 to the 0. By the way, I should mention 10 to the 0 equals the number 1, and you can ignore it when it says that on your calculator, because 1 times whatever is in front is whatever is in front. Now, when you do multiplication or division, which we're doing in this problem, you get the same number of significant figures in your answer as the number that has the lowest significant figures that you're multiplying, dividing. And all non-zero numbers are significant, So this has 4 significant figures. This has 3 significant figures. And the 1 is the definition. That's an exact number, which plays no role in there. Which of those is the lowest number? And hopefully you pick 3. So I'll let you round this off to 3 significant figures, and then I'll do it. And let's give everybody time to finish, meaning I want to get some water. And now let's do it. Keep the 5, keep the 8, keep the 9. We use the 8 to round off. Now this one's a tricky one. Watch carefully. That's 5 or greater. So I'm going to drop this, increase that by 1, which would be 0.10. Add that to 9 or to 8. And that's our correct answer. Would be 5.9 moles of sulfuric acid. And I see one of your colleagues got it right. Yay. All right, let's remember, how do we do these? Write down, what are you being asked to find? What have you given? We only had one number to start with. If we had some ratio, what units do we want our answer to be in? And use your good buddy, your good friend, unit analysis. Whatever units we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. Where do we find a relationship between moles of a compound and grams? And the answer is, in case you forgot, test number 2, important information, tells us 1 mole of a compound equals the molecular weight of that compound, and the molecular weight of that compound is the sum of all atomic weights. Remember, periodic table, the number underneath the element is the atomic weight, and you should round that off to 3 significant figures for your calculations. I'll take off a point. And the molecular weight of sulfuric acid is the sum of 2 hydrogen, 1 sulfur, 4 oxygen, H2SO4, forgot the bracket there. Add them up, you get 98.1. Do the math, remember, round it off. If I look at the time, it's time for a 5-minute break. I'm going to get up and stretch. Hopefully you do the same, and I'll see you in 5 minutes. Let's get going. All right, now yesterday I talked about one of the most important concepts I know in all of chemistry. And that is the coefficients in a balanced chemical equation give fixed molar ratios between substances consumed, reacted, and produced in a chemical reaction. And what that means is, if you look at this chemical equation, the coefficient is the number in front of the formula. When there's no number, it's the number 1. And this tells me 2 moles of hydrogen gas react with 1 mole oxygen gas to make 2 moles of water, H2O. And this is true for all balanced chemical equations. All right, let's look at this problem. And if you react 5.346 moles of oxygen gas, O2, with an excess of hydrogen gas, H2, then how many moles of water, H2O, are made? And for this problem, you are also given the balanced chemical equation. Now, the first thing is, and I'm going to do this one, but I'm going to share and let you try one too. What are you being asked to find? How many moles of water are you going to make? Moles of water. What are you given? You have 5.346 moles of oxygen. You're also given an excess of hydrogen. Whenever you see an excess of something, that means you can ignore it because you have all the chemical you need to react with anything that chemical could react with, in this case, oxygen. And you're also given this balanced chemical equation. So how do we proceed? Well, the only number I have is this number, moles of oxygen, 5.346. If I had a ratio that I convert moles of oxygen, what units do I want my answer to be in? Well, we figured that out. Moles of water. And now we'll use our good friend, our good buddy, our good friend, unit analysis. Whatever I'm trying to get to goes on top of the ratio. Whatever I'm trying to get rid of goes underneath. And now I can put that in. A 1 on top, moles of water. I want underneath moles of oxygen. And where do I get these ratio numbers? from the balanced chemical equation. And that tells me for every 1 mole of oxygen, I make 2 moles of water. For every 1 mole of oxygen, I make 2 moles of water. Now, coefficients of any chemical equation are exact numbers. So these are exact numbers. Now, before I pick up my calculator, before I do that, wait. You have moles of oxygen divided by moles of oxygen. And anything divided by itself equals the number 1, which means it's canceled out. And these units are gone, or this unit. I'm left with moles of water, which is what I want. Yay. And now I can pick up my calculator, clear it, 5.346 times 2. And my calculator gives me this number. Now, as I said previously, on test 2, it'll say, please use proper significant figures for all calculated answers. And therefore, for this one, we look here, and this is for significant figures. These are both exact numbers. So when you're multiplying and dividing, you get the same number of significant figures in the answer as the number that has the fewest significant figures. Well, exact numbers don't play a role, and therefore the only number we can use here is the 4 significant figures, and our answer should be 4 significant figures. And if I round it off, keep the 1, keep the 0, keep the 6, keep the 9, that's my 4 significant figures. Use the 2 to round off, that's 4 or less, so I'll drop that. And the correct answer here is 1.069 times 10 squared, 10 to the second power, moles of water. And that's how you do it. Remember, the coefficients, the number in front of a balanced chemical equation, and when there's no number, it's the number 1, are molar relationships. And in this equation, 2 moles of hydrogen react with 1 mole of oxygen to make 2 moles of water. Well, let's have you try one. And here you'll be given this balanced equation, sodium plus, it's not balanced. Hold on. Now it's balanced. I almost made a mistake. Bad, Dr. White. At least I caught it. 2 sodium, 1 chlorine gas, Cl2, makes 2 sodium chloride. Remember, sodium chloride as table salt or just salt. That's what you put on your food when you want it to taste saltier. All right, let's look at the following. Oops. All right, let's read this. How many moles of chlorine gas, Cl2, are reacted with an excess of sodium, Na, to make 3.7 times 10 to the fourth moles of NaCl, sodium chloride table salt? So I promise we'll do this stepwise. So first step, what are we being asked to find? What are we given? And that's your turn. And I'll send out a poll and let me know when you're done with that. All I'm asking you to find initially is, what are we being asked to find? What are we given? And it's my turn. We're asked to find how many moles of Cl2, chlorine gas. What are we given? Well, we're trying to make 3.7 times 10 to the fourth moles of sodium chloride. Notice when you see excess of something, you can just ignore it. I like those fancy hand signals. Ignore it. I don't need to think about you. Now, we only have one number to work with. That's this. We had some ratio. What would be the units I would want my answer in? Your turn. And everybody's done. So the answer is, we figured it out right here. We want to get to moles of chlorine, Cl2. Now, what units go on top and bottom of that ratio? Your turn again. Why am I doing a lot of sharing? Am I nice or what? Don't answer that. Yeah, I see everybody's done, but I'll let you have to wait while I get a drink of water. Sometimes this chemistry is very thirsty work. And now it's time to use your good buddy and my good buddy, your good friend, unit analysis. Whatever units we want to get to, go on top of the ratio. Whatever units we're trying to get rid of, go underneath or in the bottom of that ratio. And I'll write that in. I see somebody already beat me to my next question, but I'll still, for those of you at home watching this, oops, didn't want to put a mark there. What numbers go on top and bottom there? Well, that's a good question. Well, thank you. Where do we get a relationship between moles of Cl2 and moles of sodium chloride, NaCl? And the answer is right here. The coefficients, the number in front of the chemical formula, gives us molar ratios. And when there's no number, excuse me, it's the number one. And this tells me there's 1 mole of chlorine gas makes, and I'll write it over here, 2 moles of sodium chloride. And that's where, and we also have 2 moles of sodium, but we have an excess, so we can ignore that. So for every 1 mole of chlorine, and we get that from this number, we have 2 moles of sodium chloride. and we got it from here, from the coefficient. So now, before I pick up my calculator, notice moles of sodium chloride divided by moles of sodium chloride. Oops, I didn't want to write that. And remember, anything divided by itself equals the number 1. And now this cancels out these units, not the number. And the only units I have left are moles of CO2, chlorine gas, and that's what I want. Yay. And now I can happily pick up my calculator, clear it, 3.7 blue double E to get to the 4, 10 to the 4th, divided by 2. And my calculator gives me this number. And I look at this and I remember Dr. White always has on his test, please use proper significant figures for all calculated numbers. And if we look here, this is 2 significant figures. The coefficients are always exact numbers. So those don't have a roll in there. Therefore, when you multiply and divide, you should get the same number of significant figures as the number with the lowest significant figures that you multiply and divide. Well, in this case, we only have one number to look at, and this should be 2 significant figures. And now round that off, keep the 1, keep the 8, use this number to round off. Is that 4 or less or 5 or higher? It's a 5, so it's 5 or higher. I'm going to drop that, increase this by 1, and the correct answer is 1.9 times 10 to the 4th moles of chlorine. So if I want to make 3.7 times 10 to the 4th moles of sodium chloride, I react an excess of sodium with 1.9 times 10 to the 4th moles of chlorine. Now there's one problem here. What? Well, I'm going to tell you. I have never seen a measuring device that measures moles. You can go into a lab, chemical lab, you can go into a chemical plant, and you're not going to find anything that measures moles. But what you will find is a scale or balance that measures mass or weight. And now we're going to go to a much higher level problem that's real world. Yep, 10 points. And let's look at this. 10 points. How many grams of O2, oxygen gas, reacting with an excess of hydrogen are needed to make 34.6 grams of water? So what are we being asked to find? How many grams of oxygen? What are we given? We're given 34.6 grams of water we're trying to make. We have an excess of hydrogen, so we can just ignore it. And we're given this balanced chemical equation. Well, if I were to say, well, I'm going to use my knowledge of unit analysis, set up this relationship. What I'm trying to get to goes on top. What I'm trying to get rid of goes underneath. And now I'm stuck. Why am I stuck? Because I know of no way, there's no relationship between grams of oxygen and grams of water. It does not exist. So you can't do this in one step. Uh-oh, what do I do? Well, you use mass calculations for reaction. Finding the moles, or it should be the mass, not or. I don't know how that got in. Finding the mass of a substance in a chemical reaction. They need three steps. In step one, whatever you're given in weight, A, you convert to B, moles of A. In step two, using the balanced chemical equation, what we just practiced, you convert moles of A to moles of B. And finally, in step three, which we've already practiced, you go from moles of B, mass, meaning grams of B. Now, let me show you something. This will be given to you in test number 2, important information. You need to use 3 steps. So let's go back and look at this. First of all, let me erase this. So step number 1, mass of A to grams of A. When I say mass of A to moles of A, how did I get that wrong? Now, what's A? Whatever you're given a weight in. In this case, that'd be grams of water to moles of water. So how do I do that? I start with 34.6 grams of water. I want to go to moles of water. And now I'll use my good buddy, my good friend, unit analysis. Whatever we're trying to get to goes on top. Whatever we're trying to get rid of goes underneath the units. And this is moles of water and grams of water. And where do I get the relationship between moles of a compound and grams of a compound? Important information, test number 2. 1 mole of a compound equals the molecular weight of that compound, and the molecular weight is the sum of all atomic weights. And remember, you get the atomic weights from the periodic table, the number underneath, and remember, use it to 3 significant figures. So we need, for water, hydrogen 1.01, oxygen, the 3 significant figures 16.0. You don't need to see me, but there. So 1 mole equals the molecular weight of water. But we have to calculate that. The molecular weight of water is the sum of all atomic weights. And you're seeing me do this because we've already done before. Get the same number of significant figures to the right of the decimal is the number that has the fewest. In this case, 1. Keep the 0, get rid of the 2. And this is 18.0. Now, before I pick up my calculator, notice grams of water divided by grams of water. Anything divided by itself equals number 1, cancels out. And I'm left with moles of water. Clear my calculator, 34.6 divided by 18.0. And my calculator gives me the number 1.922222 times 10 to the 0. This rounds off. Notice this is 3 significant figures, 3 significant figures, exact number. So this should be 3 significant figures, which is 1.92 moles of water. Now, one thing I want to talk about when you have a multi-step calculation, in this case, there's 3. There's 2 ways of rounding off. One is round off at each step. I'm a round off at each step person. Another one is round off at the end. Now, for any question that I have multiple steps, calculations, I will have calculated for the key rounding off at each step and rounding off at the end. And if they're not the same answer, and sometimes they are, sometimes they aren't, I will accept both answers, either one, as correct if they're different, because I'm not going to force you to do my way of rounding off. And like I said, there's 2 philosophies, and I'm the round off at each step person. Now, the kind of calculation you're seeing done now today, I have done to figure out what kind of chemicals do you react for in a chemical plant to make a product in a certain amount. And I've done calculations more than once, twice, lots of times, where we're talking about $250,000, $250,000 in chemicals. And you don't want to make a mistake. I never did. If you do, you usually get fired. I never got fired. I never made a mistake. But let's go back. So we've done step 1. Are we done? No. We want to get to grams of O2. Well, it's time for step number 2. And if we look at important information, test number 2 for mass calculations, mass meaning weight, step 2 is moles of A to moles of B. Step 2 is moles of A to moles of B. Now, what does that mean? Well, where are we starting with? Water. What are we trying to get to? Something with oxygen. So what this really means is we want to go from moles of water, which we just calculated up here, to moles of oxygen, where we want to get to. Because we want to get the grams, but before we get the grams, we have to get the moles. So what do? Well, we just calculated the moles of water, 1.92 moles of water. We have a ratio. What answer do we want to get to? Moles of B. In this case, that's moles of O2. And now, if we look at this, we know it's time to use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And I'll write that in. Oops, wrong color. Let's try and get the right color. Now we'll do that. And on top goes moles of O2. And underneath, moles of water. Where do I get these numbers? From the balanced chemical equation, which is right up here. And remember, the coefficients, when there's no coefficient, it's really the number one, gives you molar relationships. And we're looking for the relationship between O2 and H2O. And if we look up here, that means 1 mole oxygen makes 2 moles water. So I now know that the relationship between moles of oxygen, moles of water, 1 mole of oxygen makes 2 moles of water. So I have 1 mole of oxygen makes 2 moles of water. And let's just check I got that right. I did. And now, before I pick up my calculator, I know moles of water divided by moles of water cancel out, because anything divided by itself equals the number 1. And I'm left with moles of oxygen, which is what I'm trying to get in step number 2. Remember, this is going to be 3 steps. So now I'll pick up my calculator, clear it. 1.92 times 1 divided by 2 gives me my calculator. But this is 3 significant figures. This is exact number. This is exact number. So my answer should have the same number of significant figures as the number that has the fewest significant figures in this multiplication division. Well, that's only the 1.92, because exact numbers are not used to determine significant figures. But wait, this is only 2. What do? Well, when you have to, put a 0 at the end. And I forgot to write, this is a -1. Are we done? Well, we've got a number in moles of O2, but if we look up here, we're trying to get grams of O2. Well, it's time for step number 3. Now you know why this is 10 points. What's step number 3? Well, let's go look at important information, test number 2. And step 3, convert moles of B to mass, which means grams of B. Moles of B to mass, grams of B. And what that really means is, for this one, moles O2 to grams O2. Remember, mass means grams. So how do we do that? Well, good news. In step 2, we just calculated there's 9.60 times 10 to the -1 moles O2. And if we had a magic ratio, what units do we want our answer to be in? Right here, or we can go way up here again, and that's grams of O2, because step 3 gives you your final answer. And now we'll use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we're trying to get rid of goes underneath. And I'll write those in. And where do we get a relationship of grams, weight or mass of a molecule, to moles of a molecule? Well, in case you forgot, 1 mole of a compound or molecule equals the molecular weight of that compound in grams, and the molecular weight is the sum of all atomic weights. Well, we're dealing with oxygen gas, O2. We need the atomic weight of oxygen. The 3 significant figures, that's 15.99. No, it's 16.0 when you round it off. So now here we know for every 1 mole of oxygen, it's the molecular weight of oxygen. Well, we've got to figure that out. Molecular weight, 2 oxygens. Each oxygen is 16.0. Multiply that, and you get 32.0. And I'll put that right here. And now I'll look at my units. Moles of oxygen divided by moles of oxygen cancel out, because anything divided by itself equals the number 1, cancels out. I'm left with grams of oxygen. And now turn on my calculator, clear it, 9.60, blue double E. Remember, use this minus sign for 10 to the minus something, not over here. Over here, I'm going to look at not that one. You want to use this one for minus 1 times 32.0. And my calculator gives me this answer. And remember, you get the same number of significant figures in your answer as the number that has the fewest significant figures. And this is 3 significant figures. This is an exact number. The 1 is a part of the definition. This is 3 significant figures. So I have to round this off to 3 significant figures. Keep the 3, keep the 0, keep the 7. That's 4 or less, so I'll drop it. And the correct answer is 3.07 times 10 to the first grams of oxygen. And that's how you do it. Now, again, this is 10 points. Can you keep a secret? Shh, don't tell anybody, but that type of problem will be on test 2. Remember, shh, don't tell anybody. That type of problem will be on test 2. And if I look at the clock, I'm almost out of time. On Monday, I will do a couple more of those problems. Also, on Tuesday, I will do chapter 5.1 problem set, along with my world famous review and the lab. Well, it's going to be a busy day. We'll get it all in. Let's go through and talk what we did again. Now, the original problem was 10 points. How many grams of O2 react with an excess of hydrogen are needed when reacting with excess of hydrogen are needed to make 34.6 grams. You're given a balanced chemical equation. You need this to do the problem. So we're trying to find grams of oxygen. We're given grams of water and a balanced chemical equation and 10 points. Yep, 10 points. There's no way you can go from grams of one compound directly to grams of a second compound. You need 3 steps. You do. And in the past, students would have to memorize it. Good news. Here are the 3 steps you need to use for that problem. The first one, the mass, meaning grams of A, whatever you're given in weight, you convert to moles of that compound. Then the second step, the moles you just calculated, you convert to moles of where you're trying to get to, that compound. And now the moles that you just calculated in step 2, use in step 3 to convert the moles of that to grams. Remember, mass means grams of B, where you're trying to get to. Now, if we look in step 1, we go from grams of water, because that's what we're given, to moles of water. Water is the A. And here's how we do it using your good buddy unit analysis. And in test 2, important information, 1 mole of a compound equals the molecular weight of that compound in grams, and the molecular weight of that compound is the sum of all atomic weights. Do the math, and we get this number. In step 2, and that's not the answer we want, because that's moles of water. Eventually, we want to get the grams of water. In step 2, if you look here, and I will, you want to convert the moles of A, in this case, that's water, to the moles of the compound you're trying to get an answer for. In this case, that's oxygen. So in step 2, we just calculated moles of A, which is water, and we want to get to, and let me fix that oxygen. That's better. Moles of water to moles of oxygen. Here's the moles of water. Here's the moles of oxygen. We want our final answer to be. We use our good buddy, our good friend, unit analysis. Whatever we're trying to get to goes on top of the ratio. Whatever we want to get rid of goes underneath. And where do we get a relationship between moles of oxygen and moles of water? We look at the balanced chemical equation. Remember the coefficients, the number in front of the balanced chemical equation formulas are molar relationships. Boy, this really is a thirsty word. And when there's no number, it's the number 1. So 1 mole of oxygen makes 2 moles of water, because the 1 here, the 2 there. And that's moles, molar relationship. So for every 1 mole of oxygen, there's 2 moles of water. And therefore, I can put in for every 1 here, mole of oxygen, 2 moles of water. These are exact numbers. I do the math, and now I have in step 2, moles of oxygen. Are we done? No, we're trying to get to grams of oxygen. So now we have to use step 3 of the need 3 steps. And step 3, in case you forgot, moles of B, what we just did in step 2, we convert to grams of B, mass is grams. So I have moles of O2, that's my B, what I just calculated in step 2. I want to get the grams of oxygen, my mass of B. I have moles of O2. I want to get the grams of O2. Use your good buddy, your good friend, your analysis. Whatever you're trying to get to goes on top of the ratio. Whatever you're trying to get rid of goes underneath. And where do we get these numbers? Well, in case you forgot, important information. 1 mole of a compound equals the sum wrong line. 1 mole of a compound equals the molecular weight of that compound in grams. 1 mole of a compound equals the molecular weight of that compound in grams. And the molecular weight of that compound is the sum of all atomic weights, which we've practiced already. So now I know, here I have moles of O2. I want to get the molecular weight, because 1 mole up here would be the molecular weight of O2. The molecular weight is the sum of all atomic weights. There's only 2 oxygen. The atomic weight of oxygen element, the 3 significant figures, 16.0. There are 2 of them. I got 32.0. Put it in there. 3 significant, 3 exact number. My answer is this. That's a big problem. That's why it's 10 points. And you should know how to do that. Now, if I look at the clock, oh my goodness, I'm out of time. I went a little longer because I got a little later start by a couple minutes. I don't want to cheat you out of any time. That's not nice. So with that, today is, wow, I got to look at my computer. It's Thursday. Tuesday off. It really felt like not a Thursday, but more like a whatever day. But anyways, it's Thursday. So that means it's the end of the week for our chemistry. Remember, a week from today, test 2. On Monday, I'll do a couple more of these 3-step problems. You should be working on the practice problems for chapter 4 and chapter 5.1. On Tuesday, because Monday I'll finish everything for chapter 5.1, I will go through the practice problem for 5.1, and I'll also do my review for test number 2, and we'll also do a lab. Well, we're going to have a busy Tuesday. With that, I'll say, gang gesund. Goodbye now. Have a great rest of the week, and I'll see you.